All right, let's go ahead and look at that problem, shall we? So we're going to take two lenses, both converging lenses, and see where the final image is. Follow the path. Ready for the problem? Here it is. All right, so we're going to take two lenses that both have the same focal points. So focal lengths, I should say, f1 is equal to f2 is equal to 30 centimeters. We're going to say that these lenses are separated by a distance of 20 meters. So we'll call the distance of separation equal to 20 centimeters, distance between the two lenses. And then we're going to say that the object P1 distance is equal to 50 centimeters. So if we want to draw this out, we're good. We're not going to do a ray diagram for it, but we can still draw it out to see how things are oriented, because the end question is, where is the final image located relative to the first lens, so as measured from the first lens. Then it wants to know the orientation, image type, and magnification as well. So we'll go ahead and do this. So let's take a different color. Here we go. Draw this out here. So we got a nice principal axis here. Sure, we've got a lens number 1 like this. I'm going to actually do it with this. This will be a little bit helpful. These two lenses are 20 centimeters apart, so there's another lens here. And then the focal length of each lens is 30 centimeters. So I'm going to do these with different colors. This is going to be f1, 30 centimeters from lens number 1, L1. And then we've got ourselves f2, which is 30 centimeters from this lens, L2, so 10, 20, 30. And there is f2 on that side. You can come on over here. Say on this side we've got 10, 20, 30. Here is f2 on this side. And then on this side, f1, 10, 20, 30 is about over here. And that's what we've got going on. This distance here, this is our distance D, which is the distance of separation between the two lenses, 20 centimeters. And then we take an object that's 50 centimeters from the first lens. So we can come over here, 10, 20, 30, 40, 50 centimeters, about right here. So here is our object. All right, so we begin figuring this out. Two lenses, there they are. What do we want to do first? Well, light's going this way, right? Light's gonna go out this way. Light going that way. So it's gonna interact with lens number 1 first. So first, do this with blue. First, look at L1 interaction. So, what do we have with this? Well, we've got that P1 is equal to 50 centimeters, F1 is equal to 30 centimeters, and we can write that Q1 is then going to be equal to the quantity of 1 over F1 minus 1 over P1 to the negative 1, which gives us quantity of 1 divided by 30 minus 1 divided by 50, negative 1, 75. 75 centimeters. All right, so 75 centimeters from this lens is where the image is produced. I did that backwards, huh? No, I didn't. Over 30, over 50. Yep, we're good. CM. All right, 75 centimeters, where's that? Well, that would be, there's 30, 40, 50, 75. That would be like over here. What would it look like? Well, we could figure it out. We would have that P is this, Q is that. It's inverted, it's enlarged in size. I'm not going to scale it on out completely, but we would have something like this. This would be image 1 due to that. Should be a little bit bigger, but there we go. There it is. Well, that's great. We can figure out the magnification of it. Yes, we're going to need it anyway. Magnification 1 is equal to negative Q1 divided by P1, 75 divided by 50, which gives ourselves negative 1.5. So I can make it a little bit bigger. And there we go. So, what do we do from here? Well, that's as far as we can go with this first one. We've got a real image, it's upright. But notice that, hey, light would have already passed through this, right? The light going this way in order to form this. This doesn't really form because this other lens is in the way. This is what would be there if this other lens wasn't there. But the light rays that would form this still interact with this. And for that reason, we still treat this as an object. So now we have this. So, drawing side of things. So this was our P1. This is our Q1. All right, so now we've got this second interaction. Lens number 2. So we've got, this becomes the object for lens number 2. This would be our P2 right there, that distance. We need to figure out what that is, but we should also notice, hey, light's going that way. This is on the back side of this lens here. Because we have that the object that we're utilizing for this interaction is on the back side of that lens, we have that its object distance, P2, is considered negative because it's a virtual object. So that's fine. What is the distance though? So the distance between these two lenses is 20 centimeters, and this total distance was 75, right? So P2, the absolute value of P2 is going to be equal to Q1 minus D in this particular case, which is equal to 75 minus 20, which is equal to 55 centimeters. So P2 itself is equal to negative 55 centimeters. So that's what we've got going on. So now we can go ahead and proceed forward and figure out the next correlation here. So we want to know, what is Q2? Well, Q2 is equal to 1 over F2 minus 1 over P2 to the negative 1. So don't forget that this is negative. So we've got ourselves 1 divided by 30, and then the negative sign in there gives us plus 1 divided by 55 to the negative 1. What happened there? 19.412 we'll call it. 19.412 centimeters. Came out to be positive. image is on the back side. Of L2. Positive Q goes to that side. But where is that? It's almost 20 centimeters from this particular lens. Now from L2, 20 centimeters about right there. So we can go ahead and say we got 19 point something centimeters right here. And then it's a matter of, well, is this going to be upright or not? We get that Q is equal to plus, so it undergoes an inversion because it's on the front side, excuse me, the back side. So in this particular case, we've got ourselves this ends up being this, got I2, final image. So, yeah. What else can we do with this? Calculate this out, right? No. We got ourselves M is going to be equal to negative Q over P, which is equal to, uh-oh, I'm messing something up. Look at this, watch. Negative 19.412 divided by P was negative 55. So look at this. It's something that I overlooked, and it's something you've got to be kind of careful with. So we've got 19.412 divided by 55. Negative signs cancel out, and we get 0.353, we'll say. 0.353. Positive magnification. M equals plus. Same orientation as the object. So it doesn't invert again. This is actually wrong. Something I overlooked because it is a virtual object to begin with. We end up with something like this. This is image 2, the final image. Again, we looked at the magnification for the interaction, right? The object was in this orientation. We got a positive magnification due to the interaction, which gives us an image that has the same orientation. If it ended up being a negative magnification, that's where you get the inversion. All right, so I need it right here. It's in the wrong spot, right? That's F2. That should be over here anyway. I was wrong a couple times, just drawing it in the wrong place. There it is. All right, so we had this then is the distance Q2. And what did we want? We ultimately wanted how far away is the final image relative to the first lens. I2 is located the distance D plus Q2, D plus Q2 from L1, which is then equal to 20 centimeters plus the 19.412, 39.412 centimeters on the backside. So there we go. That answers where's the final image relative to the first lens. The other stuff that we still could answer is, what is the overall orientation? What is the magnification? What is the image type? So let's take a look at this. So we've got the overall magnification is going to be equal to M1 times M2, which will be equal to, M1 was negative 1.5, negative 1.5, and then that is multiplied by 0.353, 0.353 equals 5 times 0.353 is about 0.529. Let's call it 0.529. So it's a little bit over half the size that it was before. Notice that this came out to be, oops, negative sign, came out to be negative. So overall, the image is inverted relative to its original orientation. That's what we drew in there, but that's what this tells us. Inverted relative to initial. Orientation. So that's that. What else do we have? Well, it is on the back side of the second interaction. Q2, I2. Backside of the last interaction, so it is a real. That's pretty much it. Physical light exists on the back side of a lens. Physical means a real image, and that's basically that. Even though we had a virtual object for the second interaction, we still end up with a real image. Pretty cool indeed. So just keep track of stuff. Draw out a little picture, scenario to make sure that you're referencing the right things, because it's easy to get mixed up with certain things. As the focal points overlap and the lenses, distance between them does definitely matter. Such things. But pretty systematic, pretty cool problems. And you think about like compound microscopes, telescopes, stuff like that has multiple interactions. How does it all work to produce this final image? Like, reflecting telescopes use parabolic mirrors and then lenses. So they use parabolic mirrors and planar mirrors than lenses a lot of times. Compound microscopes, multiple lenses. Cool stuff. All right, we'll leave it at that. You guys have a good day, good rest of the day, and keep it real. Images. Take care.